Hi, this is a brief introduction to our recent work on maximizing continuous DR-submodular functions. It will appear in NIPS 2017. DR-submodularity defines a subclass of generally non-convex, non-concave functions, but still enable exact minimization and approximate maximization in polynomial time. A function f is DR-submodular if it satisfies the diminishing returns property. If f is differentiable, dr is equivalent to the gradient being an antitone mapping. Furthermore, if f is trench differentiable, dr is equivalent to each entry of the Hessian matrix being non-positive. The general problem setting is to maximize a DR-submodular function f of x and downclose the convex constraint p. This problem setting captures a range of applications. For example, map inference of determinantal point processes, mean field inference of log submodular models, DR-submodular quadratic programming. Moreover, we have generalized the notion of continuous submodularity to capture a much broader class of functions over conic lattices. For this general maximization problem, we firstly studied its properties and found a rich structure. First of all, any DR-submodular function is concave along non-negative directions. Combined with the L-Lifshitz gradient assumption, we can have a quadratic lower bound. With a mu strongly DR-submodular assumption, we get a quadratic upper bound. More interestingly, we found a strong relation between locally stationary points and global optimum. So it's called the local-global relation. It says that x be a stationary point in P. Using x, we can define a smaller site Q. Let z be the second stationary point, but in Q. Then it always holds that the maximum of f of x and f of z is at least a quarter of the optimal function value. This conclusion can be generalized to approximately stationary points. Based on these properties, we devised two guaranteed algorithms. The first algorithm, called the two-phase algorithm, is a direct application of the local-global relation. In phase 1, it runs some non-convex solver over P to find the first stationary point x. Then it uses x to define the smaller set Q. In phase 2, it runs over Q to find the second stationary point z. Not surprisingly, it has a one-fourth approximation guarantee. The second algorithm is a non-monotone Frank-Wolf variant. It's modified from the monotone Frank-Wolf, but with a different LMO step called shrunken LMO. It has a 1 over E approximation guarantee. You can find more details in the full paper with source code at neocortex.ch.